stem from building. So here you can see that the energy use, so the operational carbon, dominates in the global context. And it looks quite similar if we look at the EU. However, in Sweden, the operational emissions have been cut down to a third from 1990 up to 2021. And this is mainly attributed to quite stringent energy efficiency requirements when we build buildings, as well as a transition from individual oil heaters over to either heat pumps or bio and waste-based district heating systems. And in combination, this has reduced the operational emissions significantly. However, on the other hand, the embodied emissions, those associated with materials and transport and the construction process, over the same period, these have been constant. So the efforts of reducing embodied emissions have fallen behind. And that's why this is the focus of this research. And we see this here on the graph, that the materials and construction, so the embodied emissions, actually are majority of emissions associated with buildings and infrastructure in Sweden. But now we also start to see adoption of energy efficiency mandates and building energy codes, as well as a move towards more renewable energy technologies for heating and electricity, also in EU and the global context. So there is a development internationally moving towards the same situation that we have in Sweden. So there's an urgent need to reevaluate the way that we build and the way that we use and maintain our built environment. So from that, in order to support this reevaluation, the research included in this thesis aims to build upon and expand existing literature, to provide a comprehensive overview and map and assess emission reductions, both current and prospective future emissions reduction and their potential across the entire construction supply chain. And it also aims to outline how these emissions reduction measures can be allocated. What's the technical maturity? How do we see them develop? And what's the timelines for implementation and strengthened adoption over time in order to aim to achieve net zero emissions by 2045. And the reason for 2045 is that's the set target for Sweden to reach net zero emissions. So it thus uses the Swedish context to exemplify the path towards net zero emissions. And when assessing these reduction potential, the research also explores the scalability of measures and illustrate the timing of implementation, as well as identifying barriers and enablers for implementation. And especially in this part, extensive stakeholder participation enriches the research. And with these in combination, the research aims to lay the foundation for actionable roadmaps towards decarbonizing the embodied emissions associated with buildings and transport infrastructure. And with that background and these research aims, I will briefly talk you through the method description, focusing on 3 key aspects of the method. The first part is extensive literature reviews. So the research has taken a broad view of literature, including not only academic literature, but a range of other types of literature in order to see what is the contemporary knowledge about emissions reduction measures and their potential. This includes industry roadmaps, company and industry plans, results from industry research and development projects, as well as different types of literature reviews, case studies, scenario analysis, both from academia and the industry, as well as different types of procurement criteria. And then, in order to identify the emissions reduction measures and test their feasibility, it has included quite integrated stakeholder participation throughout the research. And as you can see here, I'm trying here to look at what are the different stakeholders that have been participating and been engaged in this research. And that's actors all along the supply chain, starting from basic material production to manufacturers of construction products, through logistics to transport the materials to site, the actual construction process, including contractors, subcontractors, and equipment suppliers, as well as the actual design and planning phase, meaning architects, technical consultants, etc., and planning entities such as urban planning, municipalities, and other government authorities. And this inclusive approach aims to co-develop solutions by leveraging the in-depth expertise and diverse expertise that actually exists all along the supply chain. And it also is used to obtain practical experience from implementation on the ground through involvement directly obtained from stakeholders or through involvement in industry research and innovation projects and platforms. And this is also being used to then identify some of the different types of measures, which can be fuel substitution, electrification, carbon capture, recycling in the material production, and the same in the logistics, but also comes to energy efficiency and optimization in the actual construction, and then also different types of design and planning measures, such as resource efficient design, optimizing the structures to minimize the material use for the same function, and also different types of reuse of entire elements and also components, and different types of measures to prefabricate. And it's also, the stakeholder participation also serves to adjust decisions and assumptions regarding both the associated reduction potentials and when the measures are deemed to be able to be implemented and adopted to different levels, to make them as realistic and feasible as possible. And then the final key part of the applied method is a quantitative analysis. It means to tracking material, energy, and emission flows for the individual projects that I've been looking at, and also the entire sector and supply chain. And first, in a baseline or reference resource flow, that's been analyzed first, meaning looking at the material use for the specific project or for the entire national sector and supply chain, and then combining that for the different types of materials with the emission factors for that unit of material. And in the same time with the transports and the construction process, looking at the energy used for that, and combining that with the emission factors per unit of energy, which can then be, for example, diesel use in transport or heat and electricity on the construction site. And then in the next part, the emissions reduction analysis, it combines the different types of measures that either restrict the material use, so different types of material efficiency measures, such as the resource efficient design or structural optimization. And it combines that then with the material production measures, which are able to reduce the emissions intensity for the specific material production per unit of material, such as fuel substitution, electrification, recycling. And then the same thing with the transport and construction process looks at optimization measures that reduce the amount of energy needed for the same function delivered, such as logistics optimization, using the right equipment for the right activity, etc. And then also looking at the emissions factor for the actual fuel or electricity used, such as a transition towards biodiesel, for example. And all the 5 studies that build up the basis of the thesis apply the same basic methodological approach. So it integrates material emission flows, analyzes emissions reduction options and associated potentials, and also assesses the implementation timeline with increasing ambition towards aiming to reach net zero emissions by 2045. And this has been done for a road construction case and another case study looking at construction of a multifamily building, and also looking at the entire building and transport infrastructure sector and supply chain in Sweden. And there are 3 papers that looked at that. And the first paper 2 focused mainly on measures on the sort of supply side, meaning the production of cement, the production of steel, as well as the vehicle technologies used for transport and construction. And then in paper 4 and 5, the last one, been digging quite deep into more types of demand side measures, meaning what can we do to reduce the material requirements or reduce the energy requirements in the transport and construction process. And with that, I will just take you through some of the key results. And I will focus the key results on some of the obstacles and barriers that have been identified throughout the research. But firstly, I will take you through what are the main emissions components associated with buildings and transport infrastructure. And we see here a quite detailed graph of all the different types of emissions components that the research has looked into and also been able to analyze through the emission flows. But some of the key is concrete and other cement-based products, steel, and also diesel use in transport and the construction process. Together, these 3 different account for around or over 70% of the total emissions associated with building and transport infrastructure construction. So the main part of the work has been focusing on these, especially in the beginning of the research. Now, let's start with some positive results. Reaching the Swedish climate targets by 2045 is possible. That was found already quite early on in the research. It is possible for both building and transport infrastructure construction and renewal on a national level. And this was the original assessment in 2020. But we also found that for reaching the climate targets, it requires measures with longer lead times and sort of what we call transformative measures, meaning a completely new production technology or completely new vehicle technology, such as electrified excavators. And when producing cement, for example, around 60 to 65% of the emissions come from the actual chemical reactions. So in order for them to reach net zero, close to zero emissions, we need to capture the carbon. So these are quite new technologies that are needed to be implemented. And we then identified a clear need to prepare for these deeper abatement measures and associated shifts and carefully plan the pathway there. And some of the implementation timelines that we identified when the research was initiated was, for example, that introduction of steel as produced via reduction of hydrogen, one of these low carbon technologies, was expected only by or after 2040. And for cement, carbon capture, partial carbon capture, capturing some of the carbon, was expected around 2030. And when it came to heavy vehicles, there was actually battery electric heavy vehicles, for example, really heavy trucks or really heavy construction equipment. They were not even seen as possible, even by 2045. But there's been a lot of industry progress since then. If we look at, for example, hydrogen-reduced steel, now it's expected for that to be commercially available already before 2030 and reaching large supply of construction steel with hydrogen-reduced steel by 2035. And when it comes to cement and carbon capture, we actually now have looking at having the first carbon capture plant in operation in Norway already next year, capturing 45 to 50% of the cement emissions. And in Sweden, we expect to have a full carbon capture in place by 2030. And if we also look at the most accelerated development has really happened when it comes to electrification of vehicles. And here the progress, there are already heavy trucks available in commercial operations. And when we look at electrified construction equipment, There are compact, medium-sized vehicles or equipment available, but every week I see new launches of new heavier types of electric excavators, electric wheel loaders, dumpers, everything. So the development is moving rapidly, and we see that at least by 2040, a majority of electric heavy vehicles. And at the same time, there's been an increased focus on circularity. While construction steel, for example, has predominantly been produced from primary steel, there are now products on the market already with high levels of recycled steel. And with better sorting and separation, we see that there's a possibility for a majority of recycled construction steel by 2045. And we also see a development towards a more reuse of elements and products, a development. Circularity in terms of reuse was not talked about that much when I started this in 2018. But now it's talked about everywhere, and there are pilot projects and initiatives to upscale this. Same time, we see material substitution towards bio-based products for all types of products, from concrete to steel to insulation to gypsum products. And one of the most interesting I find is asphalt. So in the asphalt, you have a bitumen, which is very heavy oil-based sort of glue. And in the first road construction case, bio-bitumen was identified, but the technical maturity seemed to be very far out. But already now, there are commercial products available in operation, being paved with bio-bitumen in it. So developments have gone really fast. And also the research has developed into more detailed analysis of more materials and products, and more focus on optimization measures, as well as more detailed analysis on circular and optimized mass handling and ground reinforcement, for example, road construction projects. So with that, we actually see that close to zero emissions, not just reaching the Swedish climate targets, which is at least 85%, but close to zero emissions by 2045 is both possible and feasible if all supply chain actors do their part. And it's even possible to reach around 70% reduction by 2030. But of course, achieving these levels nationally necessitates implementation of a comprehensive measures and extensive collaboration along the entire value chain. So let's dig into deeper to some of the other barriers or obstacles that we've seen. For example, biofuels. In the first road construction case studies, it showed that it was possible already with currently available technologies and measures to halve the emissions associated with this construction. But half of that reduction would stem from using transport biofuels, so biodiesel, substituting that for fossil diesel. And the same, many industries also saw potential in using bio-based fuels as substitution for fossil fuels in their production processes. But the level of climate change mitigation from biofuels has been debated, and there's also a restriction in the actual how much supply we have of biomass and then from biofuels. So to avoid over-reliance on biofuel to achieve climate targets, there's a need to upscale other types of abatement measures. And over the course of the research, particularly in the latest paper, there's been more focus on these, on resource efficiency and circularity measures. So to demonstrate what could that mean then, we look at this one, an updated road construction case. And although the assessment form is not completely comparable, this figure still showcases the potential for resource efficiency and material efficiency, such as optimizing circular mass handling, optimized ground reinforcement, also structural optimization of the built assets, such as the bridges and other structures. And as a result of that, the broader range of measures applied, we can see here clearly that the reliance on biofuels is reduced. So the more different type of measures that we apply, the more we reduce the over-reliance on certain measures. Another obstacle has been a very sometimes heated debate between concrete versus wood. And the findings from the building case study, I hope, will contribute to valve some insights into this debate. Transitioning to bio-based construction materials can significantly reduce the emissions, but so can other measures. So it shouldn't be an either or. But building systems have historically been developed by different material production manufacturers. So they've been developed in isolation. These are the concrete-based building systems. These are the wood-based building systems. But if we look at this, which compares a concrete frame and a wood frame for the same building, how they could look like in different designs, we see that in the reference, which is this, like denoted by this number 1, that the wood frame has around 25% lower carbon footprint. But if we optimize both of these, implementing all of the measures that we see already available, we actually see here by number 2 that they are about equivalent in terms of the carbon footprint. So if we include the potential emission reduction measures, we don't see the difference. So a more relevant focus, rather than focusing on concrete versus wood, would be to selecting the right material for the right purpose. And we have recent trends also indicating a shift in this way, having more types of hybrid frames, for example, or different types of other ways of combining material where you use the best material for the best function. Last one I will focus on, I think, is the cost-effective implementation by focusing on resource efficiency. What do I mean by that? Well, I'm going to compare here what happens when we're implementing measures in different parts of the supply chain. This is also based on the same concrete frame building system that I showed in the last slide. And we see here that if we focus on primary material production specifically, meaning you substitute the fuel in the production process, or you electrify the production process, you improve the recycling, maybe you substitute some of the components, but you focus on the material production. We see that it is definitely possible to reach close to zero emissions by 2045. But a lot of this stem from what we can call sort of more high cost measures, which are these more transformative measures, such as electrifying steel production, carbon capture in the cement production, which have high investment costs. So they are quite costly measures. But then if we have a focus on more all along the supply chain, looking at what is the potential for in the design, in the structure, looking at more potential for recycling and reuse, we see that, yes, the overall reduction is quite similar. But the reduction in the short to medium term becomes quite a lot higher. As well as that, you also reduce the reliance on these higher cost measures. So by accelerating the adoptions of measures that are already available, focusing on resource efficiency and circularity, we can reach a more cost-effective transition, as we can see here. But despite this potential that we can see, there's a potential to halve the emissions already now. These current best available technologies and practices are underutilized. We see them in pilot projects, but we don't see them at scale. So barriers at the project level, such as lack of systems, structures for applying lessons learned from these pilot projects, as well as lack of incentives and knowledge gaps, are hindering implementation. So the research has actually been moving towards more collaborative efforts to advance implementation and accelerate this. And this involves collaborating with stakeholders to reach target group adaptation and trying to implement and integrate this knowledge into company roadmap and strategies, procurement templates, criteria databases, technical handbooks, etc., for the target groups of people working all along the supply chain to utilize these tools and this knowledge in order to speed up the transition. With that, I'll just end up with some key conclusions and future research. We see it's possible to reduce carbon emissions by at least 50% already now by applying available measures. It's feasible to reduce emissions by 70% by 2030 and reach close to zero emissions by 2045, but it requires comprehensive measures across the board and all supply chain actors to be engaged and be part of the transition. There is a need then to achieve this for extensive collaboration along the whole value chain. And policy measures and procurement strategies should be aligned with this to create the incentives needed. And we also see the need to act promptly to implement the strategies that are already available, as well as actively planning for and starting to implement the longer term measures. Over the course of the research, the conditions and the surrounding conditions have evolved and improvements have been made. Some barriers have been removed and others have emerged, and also same as enablers. So in the future research, what I would like to try to do is to continue working on tailoring and integrating this knowledge for it to reach the people that can utilize the research, linked to both infrastructure and buildings. And enhance this with analysis on the cost implications, trying to see if it is possible, which already started to see what role can material efficiency measures play, and also how can we see the cost developing with more strengthened regulations, for example, on the EU level. And it's likely going forward that there will be a more focus on renovating and optimizing the use of existing assets. And therefore it'd be interesting to work more on developing knowledge and practical evidence on carbon reduction measures in renovation. And another thing is that most of this research on a national level start out from an assumption on constant level of construction activity. But there could be an impact from increased level of construction. Actually, in Sweden, new indicators have demonstrated that the construction activity in Sweden have actually increased by 30% from 2008. Of course, the emissions have stayed constant, but if this is to continue, it might have an impact. And the sensitivity analysis in the national roadmap also demonstrates that it will be hard to reach, particularly the 2030 targets with an increased level of construction. So it would be interesting to explore more different types of sufficiency and planning measures that reduce the need for new construction while providing the same function. And also, as we can see, no scenario actually reach zero emissions. We get close to zero, we don't get zero. So in that sense, it would be interesting to look at the potential for an accounting of certain types of negative emissions, such as storing carbon in the built environment and other types of those negative emissions and carbon sinks. And with that, I will say thank you very much for listening, both here in the room and digitally. Thank you.